It is now time to learn how to parameterize a curve that is given to you in rectangular form. So far, in everything that we have discussed in the previous videos, we have been giving you the set of parametric equations. We have been sketching them or asking you to transform them in rectangular form. Now we're going to go the other way around. For example, here you're given the shape of a parabola in rectangular form. And now you're being asked to find the set of parametric equations that will trace through this curve. So I also came and I sketched the graph of the parabola. Pretty straightforward. The vertex is at 0, -4. The two x-intercepts are -2 and 2. And then I got two other symmetric points and I have a beautiful U-shaped graph. So now the challenge is, as I just said, how do we find x of t and how do we find y of t in such a way that they generate c of t, right? C of t is made up of two components, the x component, x of t, and the y component, y of t. And this set of parametric equations hopefully will give us the same shape, the same U-shaped. How do I find x and how do I find y? Now, before we do that, why don't we analyze the shape of this graph here? Let's note some useful information. For example, I noticed that the domain of this graph consists of every single real number. I'm going to go ahead and make a note of that. So I am noting that the domain of this graph consists of -infinity all the way to +infinity. I will also notice that the range begins, let's say, at -4 and it goes all the way towards +infinity. So making a note of that, actually this should be a pen right here. The range will be everything from -4, including -4, to +infinity. That really says pretty much that y should be greater or equal to -4. All right, but then this is the important part now, the domain. In order to begin finding the set of parametric equations, you're going to start with x. What you want is to be able to choose an expression for x in terms of t is your parameter, such that the domain of the expression for x matches with the domain of the function. We already said that the domain is all real numbers. So when I choose an expression for x, my expression for x should also give me all real numbers for x. The simplest way to parameterize this function, and you're going to even laugh, you're going to say, but that is so straightforward. And honestly, that's how it can be sometimes. The simplest way will be to let x simply equals t, where t can be any real number. Right? This is the simplest way to do that. So if you let x equals t, and I'm hoping that you can notice that the domain of this function, as I said, the domain of this function consists of all real numbers. I am hoping that you're noticing that if we let x be t and t consists of all real numbers, then t captures the entire real line again. So everything matches beautifully. Then how do we get the y component? Well, we know, right, something that we know that y is equal to x squared minus 4. That means that to get the y component, all that I have to do is a substitution of t. If y is equal to x squared minus 4 and x is equal to t, I can substitute t in place of x. So I'm going to have that y is equal to t squared minus 4. So therefore, the parametric equations will be t, comma, t squared minus 4, where t can be any real number. So this is the easiest way to parameterize this parabola, just by letting x be t. And the important thing is that by letting x be t and allowing t to cover all of the real numbers, then t also captures the entire domain of the curve. So that's what we have. Now, we also have to talk about the direction of motion, right? Because with parametric curves, with every set of parametric equations, we have to know about the motion. But let me do the motion a little bit later on. Let's discuss another way that we can parameterize this curve. Let's say that you're thinking, oh, this was too simple. It just seems even funny here. Is there a more exotic way to parameterize the parabola? The answer is yes, there is another way. So let me divide this. But remember that no matter which method you choose or which approach you choose to parameterize, the expression that you choose for x should generate all x values, because the original domain of this function consists of every single real number. So another way would be to let x equals t to the third. Why not? And again, t can be all real numbers. Actually, you know what? Let me write it like before in interval notation. T can go from negative infinity all the way to positive infinity. Why t to the third? T to the third because t cubed, again, captures all real numbers for x. If I were to quickly sketch t to the third in the traditional sense, if this is t, this is x, t to the third looks like this as a function. So then you immediately notice that all x values are captured within this parameterization. I couldn't let x be t squared, because if I let x be t squared, then you will only be getting positive x values. You will be losing all of the negative x values. So x equals t squared wouldn't parameterize this parabola. It would only parameterize half of the parabola. And if I want to capture the entire parabola, I have to make sure that I use odd exponents instead, so that I get all of the x values. All right, then now, in order to get y, I know that y is equal to t squared minus 4. So I substitute t to the third in place of x. I square that and then minus 4. So then that gives me t to the 6 minus 4. So that means that we have another parameterization of the same curve. C of t will be t to the third, comma, t to the 6 minus 4. And it's very important to specify that t will be all real numbers. So this is another wonderful way to parameterize the same curve. And I want to show you a third way, which may be a little bit surprising to you. The third way is going to involve a parametrization with trigonometric functions. Can you try to think about which trig function I can use to represent x? If I try to use sine of t equals x, then that wouldn't work because no matter what t is equal to, sine is always between -1 and 1. So then if I let x be sine of t, I would only be capturing a small part of my graph, just a section from -1 to 1. So practically just this part over here. Same thing would happen if I let x be cosine of t. That means that x would only be between -1 and 1, so that wouldn't work. Remember that here, x has to consist of every single real number. So then I think that the perfect candidate for x would be tangent. So if we let x equals tangent of t, and we don't have to use all of tangent, we're going to be strategic here. Let me take just the very first cycle of this graph. So let's say something like this. These are the vertical asymptotes for -π/2, π/2. This is t, this is going to be x. In the traditional sense, this is how the graph behaves within one cycle. And if you notice, this is perfect because now when t ranges from -π/2 to π/2, look at the x values. Every single real number is captured within that graph. So all of a sudden, I get every single value of my domain right here. So this is definitely a good way to parameterize this curve by letting x equals tangent of t and then making a note that t is going to be within -π/2 and π/2. So that means that y is going to be equal to tangent of t, we square that, -4. So y equals tangent squared of t -4. That really means that the parametrization can be expressed as tangent of t for the x component and tangent squared of t -4 for the y component, where t is within -π/2 and π/2. What a beautiful parametrization of the same curve. So now we have three different parametrizations that we can have. We can have number 1 right here, number 2, or we can have parametrization number 3 right here, the one that uses tangent. And they will all pretty much generate the same shape. The only thing is that when we use different parametrizations, you may get the same shape, but the direction of motion may differ with each parametrization. It turns out to be that with all of these parametrization, I get the same direction of motion. But I want you to be very careful though with other graphs. You may have 3 or 4 different ways to parameterize the same graph, but the direction of motion may differ with each parametrization. So you should always check the direction of motion with the parametrization that you decide to adopt. I'm going to go ahead and figure out what is my motion, what is the path with, let's say, the first one. But if you do it with the second and the third, in this case, you're going to get the same path, the same direction of motion. This is something that you can do on your own just for the sake of practice. Here I have a few chosen values for t. I chose t to be -1, 0, 1, and 2. I substituted this into the first parametric set of equations. As I said before, I was going to do only the first one right here. And once I did the substitution, I ended up getting these coordinate points. I'm going to go now and plot them so that I can determine the motion of this curve. So in doing that, the first one will be -1, comma, -3. So here is -1, here is -3, and I'm going to think of this as my first point. Then C of 0 is 0, comma, -4. I already noticed that I seem to be moving in this direction. C of 1 is 1, comma, 3, so right here. So continuing the path. And then 2, comma, 0 right here. So it's pretty much clear that the path goes like this, right? As if you're coming from the top left of the graph, you're going down towards the right, turn around, and you now keep going forward towards positive infinity. So just quickly here, I'm going to go ahead and write down that this point here, this test point corresponds to t equals, no, that was not 0, that was -1. This one here to t equals 0. This one right here to t equals 1. And this one right here corresponds to t equals 2. Here I am just summarizing some important points from our discussion of example 1, something that I want you to remember from now on, and that is going to be a theme in the next few examples that we're going to try together. Note number 1, different parametrizations of the same curve may generate different flow of motion. Whenever we try, I believe it's example 3, I think, whenever we talk about ellipses, how to parametrize ellipses, this point is going to become very obvious. You'll see there that different parametrizations will lead to different flow of motion. In note number 2, I'm hoping that you already realized that a curve may be parameterized in infinitely many ways. In other words, a parametrization of a curve is never unique, is never the only one. You may be able to do it in many, many other ways. You notice here how we started with x equals t, then x equals t cubed, and then we let x equals tangent of t. And we stopped there, but we could have continued with many other parametrizations of the same curve. In example 2, they're asking me to find the parametric equations for a circle with center 0, 0, as you can see right here on this graph, and radius r. How do I parameterize a circle like this? And then in part B, they're asking me to find parametric equations for any center, not just the origin, any center h, comma, k. Well, most of the work will be spent trying to parameterize the circle with center at the origin. So we're going to spend a lot of time trying to do A, and then B is going to follow easily from A. So let's focus our attention on A first. Here I have my circle, radius r, with center 0, 0. The easiest way to parameterize this circle is to think about trig. that will be the easiest way to find a parametrization. What I want to make sure is that every point on this circle is represented, is taken into account. I notice that the x values, they pretty much range from -r all the way to r. So I'm going to make a note of that -r is less or equal than x, less or equal than r. And the same thing is going to happen for the y values. From r on the top, -r on the bottom. So -r is less or equal than y, less or equal than r. So this is giving me a basis here. Then, remember what I said is that every point on that circle has to be represented by a set of parametric equations. So let us start by choosing a random point on the circle. And I really mean random, some x, comma, y. Well, if I pick this point right here, this point is r units away from the center. So I'm going to go ahead and denote that. R units away from the center. And it makes an angle theta from the positive x-axis, right? There is a theta associated with it. Same thing if I choose a point, random point, on the second quadrant. If I do that, this point is again r units away from the center, and it makes a theta counterclockwise from the x-axis. So I feel that I can track every point on the circle because every point on the circle is r units away from the center, and it is associated to a theta in standard form. Now I'm going to be using right triangle trig. Let me draw this as a solid line. This is a radius. I'm going to draw a tiny right triangle right here. I know that the horizontal distance is x, and the vertical distance, the height of that right triangle, is going to be y. So by right triangle trig, we know nicely that cosine of theta is going to be equal to x over r. And that immediately means that x is equal to r times cosine of theta. Similarly, sine of theta is equal to y over r, which means immediately that y is equal to r times the sine of theta. And here, notice how theta will go from 0 degrees all the way to 2 pi. If we allow theta to range from 0 to 2 pi, we pretty much capture every single point on that circle. I don't have to consider anything bigger than 2 pi. If I let theta go beyond 2 pi, I'm just going to be repeating my path on the circle. I just need to trace it once. I don't need to trace it 2 times or 3 times. So I can allow theta to go from 0 all the way to 2 pi. I am not going to include 2 pi, honestly, because 2 pi and 0 will take me to the same position. At 0, when theta is equal to 0, I am here at r, comma, 0. And then when theta is equal to 2 pi, I am back to r, comma, 0. I just need to include that point once, so I'm going to leave it there with 0. All right, so with this in mind, I think that we have found the parametric equations. Notice that theta is like t. Only that here it was more convenient to use theta because theta is kind of the universal representation of an angle. But you can switch the theta to your parameter t. So theta is the parameter. Instead of t, we're using theta. But you can perfectly switch to t if you wish. I also want you to notice that r times cosine theta, this, if you were to sketch this in the traditional sense, x is going to be between negative r and r. So that respects this domain of the circle. Same thing with r times sine theta. If you graph this function in the traditional sense, these y values are going to be between negative r and r. I'm not going to do that because I'm hoping that you can easily verify it if you wish. But intuitively, this function is between negative r and this one also is between negative r and r. So we are capturing all x values and all y values involved in the circle. So we will conclude that the parametrization of the circle will consist of r times the cosine of theta for the x component and y, not y, excuse me, r times the sine of theta for the y component. So this is going to be x of theta and this is going to be y of theta. And theta will be from 0 to 2 pi. So that's a beautiful parametrization of this circle. Okay. Now what we have to do is to figure out the flow of motion. But I think that you can already see that, right? That doesn't require a lot of work. Theta ranges from 0 to 2 pi. When theta is equal to 0, we're here are at r comma 0. Then when theta moves to 2 pi, we practically go to 0 comma r. When theta goes to pi, we're going to be here and here and here. So the direction of motion goes counterclockwise, just as theta moves on this circle. So it goes like this beautifully. Another way to specify the interval of theta is to also say, you can use the same parametrization, c of t equals r cosine of theta for the x component, r sine theta, but you can also let theta range from, let's say, negative pi all the way to pi. You can also play with the interval for theta. So what is happening here is that you're now going from negative pi, right? So you're here, and then you're moving towards pi. So you're moving in this direction all the way until you come back over here to negative r. So you practically by letting theta go between negative pi, all that you did was to change the beginning of the motion. So now you went and you decided to make this the starting point, as opposed to this one right here. If theta goes from 0 to 2 pi, you're starting right here at r comma 0 on the positive x-axis. But if you let theta go from negative pi to pi, you're starting here at the negative x-axis. But then as theta ranges from negative pi and all the way to pi, you're now moving in this direction right here. You go under to the negative y-intercept. you pass through r comma 0, you pass through 0 comma r, and then back to the beginning at pi. Notice how the direction of motion doesn't change. Now we have to tackle part B. Find a parametrization for any center, h comma k. So that means that the previous center was at the origin, but now we're moving the center h units away from 0 and k units away from 0 in the vertical direction. So horizontally, the new center goes to h. Vertically, the new center goes to k. Practically, the same translation will happen with any point on that circle. It's going to move h units horizontally and k units vertically. So, for example, if this is a typical x comma y, then under our translation, that point is going to move over here. But now this point is going to move h units horizontally, k units vertically. So it will be x plus h for the x coordinate, and then y plus k for the new y coordinate point. So then that means that if we want to get the new parametrization, we don't have to do a lot of work anymore. We just have to apply the same translation to the x component and the y component. To the x component, we apply h. To the y component, we're going to apply k. Then that means that we're going to have the old x value, r cosine of theta, but now applying the translation, plus h, comma, r sine theta plus k. And then the parameter theta is going to vary from 0 to 2 pi, or if you want, the parameter can vary from negative pi to pi, your choice. But this is pretty much how easily we can now parametrize any circle with any center. How beautiful. Now we're going to go ahead and figure out how to parametrize an ellipse. Here, we're going to start with an ellipse whose center is the origin. You can see it right here. That means that the x-intercepts are at negative a comma 0, a comma 0, and then the y-intercepts at 0 comma b and 0 comma negative b. So we have this ellipse. I know that the general form of the equation of this ellipse will be x squared over a squared plus y squared over b squared equals to 1. This is the general form of an ellipse whose center is the origin. I also want to make a note here about the intervals where x lies and the interval where y lies. So I noticed that x ranges from negative a to a, and b ranges from negative b to b. So this is something that I also want to note. So I want to note that negative a is less or equal than x, less or equal than a, and negative b is less or equal than y, less or equal than b. But it is this one right here, the first one, the significant one when choosing the expression that is going to represent x, right? I need to keep in mind that x has to be between negative a and a. It has to go as far as negative a, and it has to equal to negative a, and then it can go as far as a, and it has to be equal to a. So this is exactly where x lives. All right, so what I am going to do is I'm going to start by thinking about trigonometric expressions. If we go with trig that will be the easiest way to parameterize this ellipse. So let's think of a sinusoid, one of the sinusoids that can give us an x that is always between negative a and a. I am thinking of cosine. I drew this sketch right here where I placed t on the horizontal axis and then x on the vertical axis. And I noticed that if I use cosine to represent x, that may be a way for me to get all of the right conditions for x. X will be between negative a and a. Look at this over here. Here is your typical shape for cosine within 0 and 2 pi. And then if you look at the output happens to be between negative a and a. So again, let me highlight the output. So that's going to be right here if you notice. It's going to be exactly between negative a and a. So then that means that I am thinking of x as being a times the cosine of t. Could you have used a times sine of t? Yes, you could have. I just feel that cosine has a nicer flow. For example, if t is equal to 0, then x of 0 is going to be a times the cosine of 0, which is going to give me a. That means that the initial point of movement, if I think of a beginning, the beginning of the path, that is going to be at a comma 0. So then that means going back to my ellipse right here, this point that I am highlighting in red, this point right here. So somehow I like that start. I like to begin from the positive x-axis and then move nicely around the ellipse. You don't have to though, but I think that this is a good start. And this is the traditional start in mathematics when parameterizing an ellipse or a circle. So I think that this is definitely a great start. So I will begin here and I will say, all right, let x equals a times the cosine of t. And I think that one revolution is good enough. So t is going to be between 0 and 2 pi. I also want you to notice how I decided not to use theta, like in the circle. You can use theta. Remember, theta and t are variables. You don't have to be using t all the time. You can switch to theta. But here I wanted to switch to t again because somehow parametric equations are represented by the parameter t. So I wanted to go back to that common representation. So here is x. Now I have to find the correct y. And to do that, we're going to use the fact that x squared over a squared plus y squared over b squared is equal to 1. That means that we are going to go ahead, take the expression for x, this entire expression, and do a substitution so that we can find y. That's the goal, just as we did in previous examples. So doing my substitution will give us a times the cosine of t, all of this squared, divided by a squared plus y squared over b squared equals to 1. Then that means that a squared times cosine squared of t divided by a squared plus y squared over b squared is equal to 1. Very nicely, we can cancel a squares and we're going to be left with cosine squared of t plus y squared over b squared equals 1. My goal is to now bring cosine squared to the other side. So y squared over b squared is going to be equal to 1 minus cosine cosine squared of t, which we know by identity that the right side is going to be equal to sine squared of t, which means that y squared will be equal to b squared times sine squared of t. And then when we consider the square root of both sides, we're going to have that y is equal to plus or minus b times sine of t. So then that means that we have two possible expressions for y. That means two possible parametrizations for the same ellipse. We're going to go ahead and consider both parametrizations. We'll see how they are similar, how they are different. Here I have, again, that x is equal to a times the cosine of t. We found that y is equal to plus or minus b times the sine of t, and we are only focusing on one complete revolution, one complete path, so t is between 0 and 2 pi. I'm going to go ahead and write down parametrization 1, the first option, and then the second option. And that will all depend on the y values. So option number 1, we're going to call it c sub 1 of t. That's going to be the possibility that my curve is going to be parametrized by a times the cosine of t as the x component, and the y component b times the sine of t. Then the second parametrization, we're going to call it c sub 2 of t, is the possibility that x will be the same, a times the cosine of t, but now y will be minus b times the sine of t. And again, t in both cases is between 0 and 2 pi. So in both of these cases, these parametric equations will trace the same ellipse. You're going to get the same shape. However, if you think about the different b's, plus versus minus, there's going to be a difference. If you remember, in one of the previous examples, I said that different parametrizations of the same curve may lead to different direction of motion. And that is exactly what is happening here. These two set of parametric equations are tracing the same ellipse, but the direction of motion is different in each case. Let's go ahead and consider a few values for t. We will substitute them into the parametric equations, and then we're going to track down the motion in each case. So I am thinking of beginning with c sub 1 of 0, and then c sub 1 of, let's say, pi over 2, c sub 1 of pi, c sub 1 of 3 pi over 2. This should be good enough. So c sub 1 of 0, in the first case, is going to give us the order pair a comma 0. And then when I substitute a pi over 2, I'm going to get 0 comma b. And then for pi, negative a comma 0. And then for 3 pi over 2, 0 comma negative a. And I can already see that a comma 0 is my starting point, and then the motion seems to go in a counterclockwise manner. If I now do the same thing for the second parametrization, so c sub 2 of 0, c sub 2 of pi over 2, c sub 2 of pi, c sub 2 of 3 pi over 2, we're going to see what happens here. The beginning is the same, a comma 0. But now, for the second point, the second value for t, we're going to get 0 comma negative b. And then for pi, negative a comma 0. And for 3 pi over 2, we're going to get 0 comma negative b. So that means same start at a comma 0, but now we go in this direction. That means clockwise. Same thing over here. We're going in that direction, this direction, in that direction. So you really notice here that we get the same shape, we parameterize the same ellipse, but the direction of motion is different with each parametrization. How beautiful, how nice that is. Now, in general, the typical one, the more general parametrization is this one right here. This is the one that you're going to see in most textbooks in discussions about the parametrization of an ellipse. The one with the negative is cute, but it's just added complication because of that negative. So it is the one with the positive y, the one that tends to be used the most as the parametric equations of an ellipse. So that's the one that we are going to use mostly in these discussions. Here we now have an ellipse with center h comma k, because we know that the center doesn't always have to be the origin. It can change, right? You can have a translation of the ellipse at the origin. So now the center is any order pair h comma k. The general form of an ellipse with any center h comma k is right here. You can see the h, you can see the k next to the y. A squared is the same, b squared is the same, 1 on the other side is the same as well. How do we parameterize such an ellipse? So for example, this will be the ellipse that corresponds to that general form right there. How do we parameterize this ellipse right here that is floating above? Well, just like in the case of a circle, if we already know the parametric equations for the ellipse at the origin, all that we have to do is adjust the x and the y values of those parametrization. So here, with center at the origin, we already know the parametric equations for the ellipse. The x component, the y component, and t is between 0 and 2 pi. In the case of the ellipse that is floating over here with a center h comma k, the parametrization is going to be very, very similar. So for example, if I pick any random point x comma y on the first ellipse, the one with the center as the origin, and I track that point down on the upper part here of my ellipse, then in order to go from this point to this point right here, I just have to go h units horizontally and then k units vertically. That's all that I have to do. So if this x right here was something like 2, and let's say h is 1, I just have to go 2 plus 1 to the new x right here. And then for the y, I just have to go y plus k to get the new y value. So just as before, this point is going to have coordinates x plus h and y plus k. So that makes the new parametrization, let's say going from the original one to the new one, that's going to be a times cosine of t plus h, comma, b times sine of t plus k, where again t is going to be between 0 and 2 pi. Okay. From now on, you will never have to repeat all of the steps that I just did for you. I did it just to show you where the parametric equations come from. I think that if you know the reason behind the why, it becomes easier and it strengthens your understanding of the entire concept. But what you need to remember now are the final results. These are the parametric equations for an ellipse whose center is at the origin. These are the parametric equations for an ellipse whose center is h, comma, k, something other than the origin. They're very similar. The only difference is that one has the h and the k if the center is not the origin. And then in order to complete one revolution around the ellipse, t is allowed to be between 0 and 2 pi. If you increase the interval for t, you're still tracing the same ellipse. That just means that you're going to go around the ellipse several times. That's all that it means. Now that we know how to parameterize an ellipse that is centered at the origin or centered at any other point on the xy plane, I think that we're ready to tackle example 3. Example 3 is asking us to find parametric equations that trace out this ellipse. Here is its graph, where t is the parameter in seconds. So now the units of time are clearly in seconds. The motion around the ellipse is counterclockwise, so in this direction, and it must begin at the point 2 comma 0. The point 2 comma 0 is right here. Let me put a heavy dot around it. That's not a problem, right? Both of our parametrizations of ellipses began there at that point. Let us begin by writing down the general form of the set of parametric equations. We know that c of t will be equal to a times cosine of t, and the y component will be b times sine of t, and we know that t is going to be between 0 and 2 pi. This is telling me practically that the period of this curve is going to be 2 pi. This is clear. I know that you know that. I just want to write it down here for the record because the period is going to change in parts B of this problem. Now, I also want to make a note of what is A and what is B. We obviously, if you notice, we need it here and we need it here as well. So that I can determine by looking at the equation given to me of the ellipse. I know that I have x squared over 4. That is like having x squared over 2 squared, meaning that A is going to be 2. I'm going to make a note of that. I'm going to note that A is equal to 2. Similarly, I have plus y squared. That's like having y squared over 1 squared, which tells me that B is equal to 1. And just a note here, since A, being the horizontal radius, is bigger than B, which is the vertical radius, I expect the long part of the ellipse to be along the horizontal axis. And that's what you see over here. See how the ellipse stretches horizontally instead of vertically. All right, so now writing down the set of parametric equations for this ellipse, we are going to have 2 times cosine of t, comma, sine of t, where again t is going to start from, is going to be in the interval 0 to 2 pi. And just to quickly test what they wanted us to be satisfied, they wanted the ellipse to begin at the point 2 comma 0. So let's quickly check that. T begins at 0. So then we would have c of 0 equals to 2 times the cosine of 0, comma, and then over here sine of 0. So then that will give me 2 times 1, which is 2, and the sine of 0 is 0. So that requirement was satisfied. Another thing that we have to satisfy is the direction of motion. It must be counterclockwise, as specified in the original problem. I don't have to go ahead and choose values for t and then create a bunch of coordinate points and then check the motion of those points. I don't have to do that because I already chose the set of parametric equations with the y component positive. I chose the one that has just b sine t. And I know that for this particular choice, the motion of this curve is indeed counterclockwise. If I would have chosen the other choice, the one where the y component is negative b sine t, then that would have been incorrect because this particular parametrization would have the opposite motion. But by choosing the positive option, then I already know that I have the motion that they want in the problem. So I know that my motion will be counterclockwise, and I can just go ahead and write down the arrows. In part B of the problem, they are now describing a different scenario. They say that the motion around the ellipse is counterclockwise. So that is going to be the same. Begins at the point 2, 0, that's also the same, and requires 1 second for a complete revolution. Now this is different. They're changing the period on us. The period is no longer 2 pi. The period here is 1. That means that somehow we're going to have to readjust the set of parametric equations that we already have at our disposal. We're going to have to make some sort of modification. Can you start thinking about what that would be? And meanwhile, however, let me go ahead and highlight the important information. I don't want to forget to check all of these components. Counterclockwise, this is easy. We're going to go ahead and choose the set of parametric equations with a positive y component. It begins at the point 2, 0. I think that's also going to be straightforward based on what we already have. Most of our parametrizations begin at a, 0. That one that is different is this one right here, the period. It should require 1 second for a complete revolution. When the period is 2 pi, hopefully you already know the correct parametrization for this ellipse. So let's write that down. We just used it in part A and we developed these parametric equations before part A. So when the period is equal to 2 pi, you already know that the set of parametric equations are equal to a times the cosine of t, comma, b times the sine of t. But here t is between 0 and 2 pi, right? This is because the period is equal to 2 pi. And to have a counterclockwise motion, we want to make sure that we choose the positive component for y. But if we change the period, if the period now needs to be 1, then we are going to have to adjust our parametric equation. It will no longer just be a cosine of t, b sine of t. If we change the period, that change will be demonstrated somehow. That change will show here within the angle. That means that the coefficient of t won't just be 1 times t. Here is just 1 times t. This coefficient right here is going to change if we change the period. So then the new general form is going to be c of t equals a times cosine of b. No, let me not use b because we already use b. I know that in pre-calculus, most likely you were using bt, b inside, but here is not a good idea to do that. So let's do c. ct, comma, b times the sine of ct. close brackets. And now we know that t has to be between 0 and 1. So that length, that period has to be equal to 1. This is why we know that this must be the interval for the parameter t. So what we need to figure out now is what will c be equal to if we need to have a period of 1. What will c be equal to? Here, you must remember something from your studies of trigonometry in pre-calculus 12 last year. You must remember that period is equal to 2 pi over this coefficient c. This is how the period is measured. And if you don't remember why that is the case, let me give you a quick reminder, a quick refresher of why the period is equal to 2 pi over c. It's definitely worth remembering. If I just have cosine of t, we already went over this, the period is 2 pi, as simple as that. But if we have cosine of 2t, for example, what is the 2 really telling us? The 2, the coefficient of t here, these 2, what we are now calling c, 2 is telling us that within 2 pi, I will now have 2 cycles of my graph of cosine. That means that I'm going to see 2 perfect cycles between 0 and 2 pi, meaning that the period is going to be pi. There's going to be one cycle from 0 to pi, and then another identical cycle from pi to 2 pi. So then that means here period is pi. In the original one, the period was 2 pi. Let's do one more. What if we had cosine of 3t? If that was the case, again, from 0 to 2 pi, the 3 is telling me that now I am going to have 3 full cycles within the same interval, 0 to 2 pi. So 1, let's pretend that they are identical. So here is going to be 1 cycle, the second cycle, the third cycle. That means that this first mark is going to be 2 pi over 3, and then this is going to be 4 pi over 3, and then 2 pi. So then we know that the period is equal to 2 pi divided by 3. I want you to look at the pattern now. When the period is 2 pi, that's because we had, let me use a different color, p equals 2 pi over 1 because c was 1. In the second case, we had p equals 2 pi over 2 because there are 2 cycles within 2 pi. And here we have 2 pi over 3 because there are 3 cycles within 2 pi. So then the period is always going to be 2 pi over the value of c. So this is where this expression is coming from. What we now want here is the period to be 1. So that should allow us then to find c. If we want the period to be 1, if we're changing the period from 2 pi to 1, we have to change c. So if the period is 1, we're going to have 1 equals 2 pi divided by c, and then cross multiplying, that means that c is equal to 2 pi. So then this is our set of parametric equations. Our set of parametric equations will be a times the cosine of 2 pi t, comma, b times the sine of 2 pi t. where t is going to be between 0 and 1. And the last thing that I have to do now is to insert the correct A and the correct B, but that will be the same from before. We're not changing A and we're not changing B. So then C of t is going to be, I believe that A was 2 cosine of 2 pi t, and B was 1. So sine of 2 pi t, comma, where t is within 0 and 1. So very, very nicely, we found our parametric equations for this scenario. What we have to make sure is that we are starting at the point 2 comma 0. So that's an easy investigation. C of 0 is going to be equal to 2 times the cosine of 2 pi times 0 is 0. And then sine of 2 pi times 0, 0 again. So then that's going to give us 2 comma 0. That checks nicely. And again, the direction of movement, we don't have to check that because we already chose the y component to be the positive option. So that already takes me in a counter-clockwise motion through this ellipse. The final part of this problem is now going to describe a different scenario. It's actually going to have different requirements for us. See, the motion around the ellipse is clockwise. That's different. Begins at the point 0, 1, and it requires 2 seconds for a complete revolution. So let me highlight the important components here so that I remember what I need to satisfy. The motion has to be clockwise, something different here. The beginning must be at 0, 1, again different. And the period must be 2 seconds. So 2 seconds for a complete revolution. That's also different. I am hoping that you are now realizing that the set of parametric equations that we build and that we used in parts A and part B are going to be a bit useless here. And that's mainly because of the starting point. In those set of equations, the starting point was always located right here at 2 comma 0. But now they want the starting point to be here on top, right there. So if the starting point needs to be 0 comma 1, then that means that the parametric equations that we have starting with t equals 0 are not going to work. So if we need to begin here at the very top, then what do we do? Well, there are two things that we may be able to do. One is to create a different expression for x and do the entire analysis and build a new set of parametric equations. And two, sometimes another option will be to play with the interval of the parameter. Instead of being from 0 to 2 pi, maybe we can change that into something else. The reason why we're not going to be able to take option number 2, which is to play with the interval of the parameter, is because here the parameter has been set for us. The parameter has to be 2 seconds. That means that it has to go from 0 to 2. I'm going to write that down here. So I know that t has to be between 0 and 2, right? We know that. That is really telling us that when we compute c of 0, we must get the point 0 comma 1. That's a must. So again, we have to be here on the top part of the ellipse when t is equal to 0. So because the interval of the parameter has been fixed for us, I'm going to have to go ahead and try to follow option number 1. In other words, we need to rebuild a new set of parametric equations. Our new parametrization will still consist of trigonometric functions. We're going to continue the rhythm of trig. But now I have to begin by finding a new expression for x. So here I have the possibility of x equals a times sine of t, and x equals a times the cosine of t. We already know pretty much that the second option is not going to work for us because this is practically what we had before. But let me tell you again why. Just want to make sure that we are all together here. The beginning has to be the point 0, 1. That means that x must be 0. If I take the cosine graph, this one right here, when t, notice over here how again, in the traditional sense, I place t along the horizontal axis, x goes along the vertical axis. If t is equal to 0, the beginning, the x value is going to be a, exactly a, and a is equal to 2. So that takes me, I'm going to go back to the ellipse, that takes me right here. I don't want x to be a. I don't want that. What I want is for x to be 0, is what they want me to have now. So I feel that we're going to have to switch things around and use sine for x instead. When in the case of sine, when t is equal to 0, we are here at the origin. That really means that x is going to be 0, and that's what we want. So then, what we are going to do is to pretty much let x equals a times the sine of t. In our case, a is 2. I'm going to say 2 times the sine of, but I also need to figure out c because we have changed the period. So let me quickly do that here on the right. I know that the period p is equal to 2 pi divided by c. The period is equal to 2. So 2 equals 2 pi over c. Cross multiplying, 2c is equal to 2 pi. So then c is equal to pi. So going back over here, I am going to have pi t as part of that expression. So x is going to be equal to 2 times the sine of pi t. Now that I have a new expression for x, I'm going to have to go ahead and substitute this expression into the equation of the ellipse. I'm going to do that in order to find the y expression. Here I have the equation of the ellipse. Notice how I am substituting 2 sine of pi t into x. Then I go ahead and I square, I cancel things out. Then the goal is to solve for y, so I'm isolating y squared. When I do that, I get that y squared is equal to 1 minus sine squared of pi t. And then I use the identity that says that this expression is equal to the cosine squared of pi t. And then the square root of both sides takes me to two possibilities for y, plus or minus cosine of pi t. So now that I have two possibilities for y, I know that I have two possible parametrizations for this ellipse. What I have to do now is to choose the y expression that is going to satisfy the direction of motion. Most likely, one of these expressions will have a clockwise direction of motion, and the other expression is going to have a counterclockwise direction of motion, just like in the previous discussions at the beginning of this problem. So I'm going to end up choosing the one that gives me a clockwise motion. Here I have written down the expression for x and the expressions for y, and the parameter is within 0 and 2. What I have to do now is to investigate motion. I am going to start by choosing the positive expression for y. I am going to plug in a few values for t and then track down the motion on the ellipse. If I don't get a clockwise motion, then I'm going to go ahead and try the negative expression for y. That's my plan. Here I have some of those points. I started with t equals 0, and I immediately got 0, 1 as my starting point, and that makes me very happy. Let me go ahead and start marking that down. So I'm going to make this point green now, right here on top. That's the starting point. Then I tried t equals to 1/2. That allows me to get the 0.2 comma 0, and that again makes me extremely happy, because now, as if indeed I am moving in the clockwise motion. But that's not enough. I want to be really sure here. So I try a third point. When t is equal to 1, I end up getting 0 comma -1. So now I'm pretty much convinced that indeed the motion on my ellipse is going to be clockwise motion. That's what I wanted. So then I don't need to waste time checking the negative expression. The other expression may give me the opposite effect. So right away, I know that I have found a parametrization satisfying all of those three conditions. C of t is going to be equal to 2 times sine of pi t, and the y is going to be cosine of pi t, where t is going to be between 0 and 2. Last example. Now let's go back to something easier. Parametrizing lines. I'm going to begin with part B instead of A. I think it's going to be a nicer way to begin here. Find parametric equations for the line y equals -2/3 x plus 1. I am going to show you two ways to do this. Approach number 1 will be the approach that I took in this entire video since the beginning. And approach number 2 will be by utilizing a theorem that appears on the book. You actually don't have to use that theorem to parametrize lines, but I'm going to go ahead and discuss it because it is there, because you may find it interesting. But the easiest way to parametrize lines is just by thinking of an expression for x, plugging that expression into the equation, and then figuring out the y expression. So following the same process with b first, we have here y is equal to -2/3 x plus 1. This is a simple line with an infinite domain. In other words, we know here that x is going to be between, well, it's going to be -infinity to +infinity. So all real numbers. Same thing for y. Y, the domain for y will be from -infinity to +infinity, all real numbers. But it is the first condition, the one that is very important for us to satisfy as we choose an expression for x. Now, the simplest way to parametrize this line is to just let, so I'm going to put here first parametrization, is to let x be equal to t. Again, realizing that t is going to be between -infinity to +infinity. So if we let x be t, that means that y is going to be -2/3 t plus 1. So therefore, c of t is going to be t comma negative 2/3 t plus 1. This is the simplest way to parameterize. Another way is to let x equals t to the third. And t to the third is allowed because t to the third covers all real numbers again, right? So then that means that I am not sacrificing any x value. Remember, the domain of x has to be all real numbers. When I let x equals t and t is allowed to be all real numbers, I am covering all of my x values. If I use x equals t squared, that's bad because t squared will consist of only positive numbers. So I am only going to have a piece of my line. I will not have the entire line. So I have to work with odd exponents here. And again, if I let x equals t cubed, then t is going to be between negative infinity to positive infinity. So then y is going to be negative 2/3 t to the third plus 1. Therefore, another way to parameterize is to use t to the third for the x component and negative 2/3 t to the third plus 1 for the y component. Okay, so straightforward. I can go forever. My goodness, I can have infinitely many parameterizations of the same curve. This is another example that parameterizations are not unique. You don't have just one single way to parameterize a curve. You can parameterize it in infinitely many ways. The only thing that is going to differ with each parameterization, or actually I should say the only thing that may differ, is the direction of motion, right? Different parameterizations may have a different path on the same curve. So this is one of the things that if you're producing a graph, you have to make sure that the correct direction of motion is identified for a specific parameterization. Part A is asking us to find the parametric equations for the line through this point with slope 4. They didn't give us the equation of the line, but we can easily find that. I'm going to use the point slope form of a linear equation. Y minus negative 1 is equal to 4 times x minus 3. That means that y plus 1 is going to be equal to 4x minus 12. Y is going to be equal to 4x minus 13. So that's what I have. Now, parameterizing becomes straightforward. The simplest way to parameterize this curve is practically then to let x be t. So then you would have t, comma, 4t minus 13, where t is going to go from negative infinity to positive infinity. And then the other way, just as we did in the previous part, we are going to let x be t cubed. It cannot be t squared because then t squared will only generate the part of the line that has positive x values. And we want to go beyond that. So we can let x be t cubed. So that means that the y component will be 4t to the third minus 13, where t again goes from negative infinity to positive infinity. I'm going to stop there because I know that I can have infinitely many ways to parameterize this line. I just have to provide, actually I only had to provide one, but I gave you two. Here is theorem 1. In the textbook, this is theorem 1, parameterizing a line. This will give us another way to parameterize a line. Consider the line passing through a point P that has coordinates a comma b. And this line has slope m, which is s over r. practically then what we have is a random point. I'm going to position it here on this line where this is A and this is B. So we know a point on the line and we know the slope of this line. The slope is equal, M is equal to S over R, the rise over the run. So we know that. We know a point and we know the slope. If you remember, part A of the example that we just did was like this. We knew a point and we knew the slope. What we did there was to find the equation of the line. With this theorem, we are not going to have the equation of the line. This theorem says that, so this is now what the theorem says. It says that we can let x equal to a plus r times t. Again, what is a? A is the x value of the given point, and r is the run of the slope, right? We can go ahead and let x be equal to a plus rt, where here t is going to be, again, between negative infinity and positive infinity. So t is going to be an infinite parameter. And I'm hoping that you are not finding this strange. We can perfectly let x equals a plus rt. In the traditional sense, this is a great way to parameterize this line. I know that it seems weird, but it is perfectly fine. Look at this. In the traditional sense, t is going to be along the horizontal axis and x is going to be along the vertical axis. My goodness, and a plus rt is just a line, right? It's a line here. The y-intercept happens to be at 0, comma a. I don't know what a is, but pretend if the slope here will be r. If the slope is positive, your line is going to look like this, and this is going to be a. If the slope is negative, let's say your line is going to be decreasing. But no matter what, look at this. If we let the expression for x equals a plus rt, those lines will give us every single x value, right? And that's what we want. The original line has an infinite domain. X consists of all real numbers. If we use this parametrization for x, then again, we are going to get all x values. In fact, let me go and highlight over here the vertical axis. So that's a fine parametrization. There's nothing wrong with that. You need to remember that you can choose any expression for x as long as you keep the desired x values. So if we begin with this as our x expression, then what is the y expression? What is the expression for y? I can just come and give it to you, just like in the theorem in the book, but I want to go ahead and kind of develop it for you. In a sense, we are proving the theorem. It's such an easy development that why not? So instead of just giving you the results of the theorem, giving you why don't we go ahead and find it? You know how to do it. We did it for the ellipse. We did it for the circle. It's the same process. The process we've done numerous times already in this video. So if I am starting with this as my x expression, then I need to go ahead and figure the y expression, and I am going to do that by substituting this x into the equation of the line. Now, because I don't know exactly what a is equal, what b is equal, what is the slope, I am going to be working with only variables. Using the point slope form, we know that this will be y minus b. This will be the equation of this line. y minus b equals to the slope times x minus a. So this is the equation of this line in point slope form. Now I will do my substitution of the expression for x. So y minus b equals s over r, substituting x with a plus r times t minus a. Notice how the a's will cancel out, and I am going to have y minus b equals s over r times rt. Nicely, r's will cancel, and I am going to have y minus b equals st. So y will be b plus st. And here is the expression for y. How lovely. So this is telling us then that the parametrization or another parametrization of this graph will be a plus rt for the x component and b plus st for the y component, where t is between negative infinity, positive infinity. So I honestly don't care if you do the parametrization of a line with this theorem. If you want to do it that way, beautiful. Just memorize the parametrizations and then you have it immediately. Again, let's study the format. For the x component, we have a, and a corresponds to the x value of the given point. And then for the y component, we have b. B corresponds to the y value of the given point. Then we have r plus rt for the x component, and r corresponds to the denominator of the slope, right? And kind of that makes sense. The x goes with the x. After all, the slope is equal to delta y over delta x, the change in y over the change in x. So in this case, a corresponds to the x value of the point, and r corresponds to the change in x of the slope, x's with x's. And b, same for y, the same thing. B corresponds to the y value of the given point, and s corresponds to the numerator of the slope, y with y's. If I now apply this theorem to part A of the example that we just did, it will look like this. In the example that we did, part A gave us a point, p equals 3, comma, negative 1, and the slope was 4. I'm actually going to put 4 over 1. 4 is going to be s, and then we are going to have here that 1 is going to be r, 3 is a, and negative 1 is b. So then the parametrization, or a third parametrization of the same problem, would be 3 plus t, and then negative 1 plus 4s, where we know that t is within negative infinity, positive infinity. That's an easy way to do that. Then in part B, if you remember, they gave us the equation of the line. But I can still use this theorem, because if I have the equation of a line, I know a point on the line and I know the slope. In this case, if you remember, this was the equation that was given to us. In this case, a point on the line would be the y-intercept, the point 0, 1, and the slope is negative 2/3. So I can think of negative 2 as my s, and I can think of 3 as my r. 0 is going to be a, and 1 is going to be b. So now you can put these values into this expression right here. I think that you can handle that. I don't think that I need to do that for you. part B of the theorem is telling us that if we consider a line that happens to pass through 2 points, A comma B and C comma D. So now they're giving us 2 points. They're not giving us explicitly the slope. Even though we can find the slope, they're not giving us the slope. They're giving us 2 points on that line. So here I will position them randomly. Here is point P. Point P has coordinates A comma B. And here is point Q. It has coordinates C comma D. What the theorem says is that the expression for x can be allowed to be A plus the parameter t times C minus A. Again, I know that it looks strange, but even though this expression for x looks a little bit complicated, it is still a line. That means that you're still capturing all x values. Again, we are assuming that the domain of this line consists of every single real number. And let's examine the construction here. We begin with A. A is the x value of point P. Then we have the parameter t times C minus A. C is the x value of the other point, of point Q. So we end up subtracting those two x values, the x value of Q and the x value of P. So if this is our expression for x, we are going to let t go from negative infinity to positive infinity so that we can capture all real numbers for x. Because remember, this is the domain of this graph, all real numbers. This is another linear expression that captures all real numbers for x as well. So if we now try to find y in the same way as we did it before, so imagine that we do the proof. I can just give you the expression for y, but I want us to be able to do it together for you to see where y is coming from. We're going to start with the point slope form of the equation of the line. That means that we're going to have, we can choose any of those 2 points. I'm thinking choosing point P. So we will have y equals, no, I'm lying, y minus b equals to the slope times x minus a. Now the slope, I'm going to have to do better than that. The slope here is going to be d minus b divided by c minus a. So then we are going to have y minus b equals, substituting d minus b over c minus a, and then doing another substitution for x, that will be a plus t times c minus a, and then minus a right here. So some things that are going to cancel, a with a, that will give us y minus b equals d minus b over c minus a, that won't change, times t times c minus a. But then very nicely, c minus a will cancel, and we're going to have y minus b equals d minus b times t. That's practically what we have. Fantastic. So y is going to be b plus, let me change the order of the factors. So t times d minus b. And this is exactly the expression for y. So the parametrization of a line given 2 points on the line will be a plus t times c minus a, comma, b plus t times d minus b, where t happens to be between negative infinity and positive infinity. If you are willing to remember these expressions, beautiful. You can always use them. I honestly forget them. I do. So if I am given 2 points on the line, I find it easier to find the equation of the line and just to let x be t or to let x be t cubed. I find that process easier because it relies less on memorization. But if you have a photographic memory or anything like that, and you can easily remember these expressions, then you don't have to find the equation of the line. Given 2 points on the line, you know that this is exactly how the a particular parametrization is going to go. So go for it, use it. Something really quick that the author also mentions on Theorem 1. He mentions this as a by the way, as the last phrase on the theorem, is how do you parametrize just a segment? One second. Just this segment, this piece of the line, the segment going from P to Q. Imagine that you ignore everything else. Just a piece that goes from P right here to Q. Do you have to do something special, something different? Do you have to build a new set of parametric equations? The answer to that is no. If you use this set of parametric equations right here, all that you have to do is to play with the interval for t. So if I just want this segment, all that I have to do is to let t run from 0 to 1. Honestly, that's all that I need to do. If I restrict the parameter t to be between 0 and 1, including 0 and 1, I am only going to get this piece of my line. And a quick check will be checking the endpoints of the interval. What is C of 0? C of 0, again, I am using this parametrization. C of 0 is going to be A plus 0 times C minus A. So that will just give me A. And then into B, I am going to have B plus 0 times D minus B. So again, that will just give me B. So notice how when t is equal to 0, boom, you get point P. And then you can try c equals to 1/2. Now in this case, because we only have variables, it's going to be a bit meaningless. So I'm going to skip and I'm going to go all the way to 1. So c of 1 is going to be, let's see, when t is equal to 1, we are going to have a plus c minus a for the x component, and we are going to have b plus d minus b for the y component. So then that means a's will cancel here, b's will cancel here, and we are going to have c comma d. That takes me beautifully to my point Q. So trusting that everything in the middle is going to behave nicely, if we restrict t to the interval 0, 1, we only parameterize the piece of the graph that begins at P and let's say ends at Q. And the direction of motion in this case seems to be in this way, climbing towards the climbing upwards on the line. But if you don't restrict t, if you let t consist of all real numbers, this set of parametric equations will trace through the entire line. They will parameterize the entire line.